Good morning, everybody. This is another seminar, another colloquia that we organize here at the Instituto de Astrofísica de Andalucía. And today we have Dr. Eva Schinnerer from MPI in Heidelberg in Germany. And she will talk about the star formation process on cloud scales in nearby galaxies. Our scientific director, Isabel Marquez, will introduce her. Please, Isabel.
Good morning, everybody. Thank you very much for being here in this Weblogia program. Thanks a lot to all of you, in starting with our speaker, because we all know that that is in these difficult times. We are very grateful for all of you. Dr. Eva Schinnerer is a staff scientist at the Max Planck Institute for Astronomy in Heidelberg, Germany since 2004. She made her PhD in astronomy at the Ludwig-Maximilians University on the psychonuclear dynamic and star formation in two representative Seyfert galaxies. During her PhD, she worked at the Max Planck Institute for Extraterrestrial Physics in Garching, in Germany as well. And after that, she has performed several postdoc contracts at the USA, mainly in the California Institute of Technology, in Caltech in Pasadena, and the National Radio Astronomy Observatory, and where she has also worked as adjunct associate astronomers in 2011. And now, as I said, it's a staff scientist in Heidelberg, where she got an ERC advanced grant concerning the physics of star formation and its regulation in 2016, and she's a group leader of the extragalactic star formation at the MPAIA. She has a leading role and a participation role at the highest level in several actual or past surveys that are very interesting from the point of view of studying the physics of galaxies, as the FANGS survey, which means physics at high angular resolution in nearby galaxies. She was the PI of the VLA Cosmos, so the Cosmos Evolution Survey, and the PI also of POSE, the Plateau de Bure Interferometer Second Whirlpool Survey for M51, in the S4G, and the GAL, Keyfish, Laduma, Nougat, Lemons. So the most important surveys being made for study galaxy evolution. She's author of about 380 referred papers with more than 23,000 citations, so an index of 82 as ADS. Her fields of interest are star formation through cosmic times, evolution of active galactic nuclei, state and dynamics of interstellar medium, and millimeter radio interferometry, where she is an international reference. Today, she will talk about the star formation process on cloud scales in nearby galaxies. And just before she starts, I'd like to acknowledge her, to thank her a lot for accepting our invitation to give this talk today. So thank you very much, Eva, and that's your turn.
Thank you very much, also for giving me the opportunity to basically tell you about some of the highlights from the ongoing FANGS survey. Before I want to do that, I want to basically motivate why it is interesting to look at the star formation process in nearby galaxies on the scales of about molecular clouds. So, the star formation process can also be thought about as a cycle of baryons in galaxies. And here you can see a representation of what this means. So you basically start off with the cold atomic disk in the galaxies that are present everywhere. At some point, this gas has to condense and it starts to become molecular clouds. So entities that are already more gravitationally bound are forming. Once they've formed, you can have the onset of star formation within the clouds, and once massive stars, OB stars, have formed, those become visible as H2 regions, so in very early stages of the star formation. After the H2 regions have died off, your stars will become visible also as young stellar clusters, and these stars during the formation already have their own stellar ejecta or also supernova remnants where they inject back into the material, into the interstellar medium both metals, but also again dissociated all the molecular gas that is there. So you're back to neutral the gas, and then the cycle can basically start again. So as part of today, since this is a very large, I would like to focus only on the upper half of this cycle. This is basically going from what can be learned from molecular clouds, and here I'll focus on tracers, the carbon oxygen only, that is basically tracing the bulk of a molecular gas. You also have the other molecules available that are more sensitive to higher volume densities, and that would then be maybe tracing regions that are even more closely to star formation to happen. For H2 regions, a very prominent tracer is the H-alpha line, which is basically one of the most prominent hydrogen recombinations lines that can be observed in the optical. However, there are also other ionized atoms or lines that can be observed and can be used to basically infer something about the properties of these H2 regions, such as their metallicity, their ionization state, and others. And then you can also look at the end products, but I will be more ignorant of those today. So why looking at the star formation process? So the tracers I've shown you, you can observe them, for example, in the Milky Way. So this is an image of the Orion, one of the brightest star forming regions, or most well studied in the Milky Way. And they have a size of about a few 10 parsecs. So in principle, for what I'm talking about, what you see here is basically a pixel in hours. So it's basically a star formation unit. The Milky Way offers you the chance that you basically can understand very detailed physics that are going on. So you see that the radiation is impacting the surrounding ISM, as well as how the ISM indeed might collapse and form individual stars. On the other extreme, how you can study the star formation is if you go out to the early universe and you start to look at galaxy populations. And the advantage of doing this, here you see, is that you get an idea how galaxies as such have evolved, how star formation has been important in shaping the galaxies and the universe as we see it today. And in this HST image from the ultra deep field, you see that galaxies come in different flavors, with being red galaxies where little or no star formation is available, to galaxies with blue that are very active in star formation. So why is it important to look at nearby galaxies? And that is basically where you can bridge the understanding of the detailed physics and connect them to the evolution. Nearby galaxies like M51 that is depicted here offer you the opportunity to understand if the environment within the galaxy is important. So that is, if spiral arms play a role, if a stellar bar has an impact, what's the impact of an active galactic nuclei? And also you get access to key parameters like stellar surface density, gas surface density, star formation rate, surface density, so you can resolve it. So you basically studying the boundary conditions or initial conditions that would go into the detailed physics. So this is basically the motivation why nearby galaxies are important and what is their key role in our global understanding of the star formation process. So for the course of this talk, I would like to focus basically on two sets of questions. As I said, the stars basically have the cold clouds that you have a cold neutral gas disk in a galactic disk, and that forms molecular gas. And so the first one interesting question is, what is the physical state of this molecular gas? Is it all bound? Is it more diffuse? And also, is it always at the same level? And the other question is basically, what sets this state of a molecular gas? So is it just a global parameter, or are local environmental conditions, do they play a role as well? And the second aspect basically concerns the transition from the clouds to them forming stars. So where the gas within the cloud starts to collapse and form stars. So where does star formation happen? Does it happen everywhere throughout the disk? Is the process, how efficient is the star formation, so the conversion of the molecular gas into the stars? And how fast does this proceed? So how long does it actually take for a cloud to start forming stars? stars. So these were all questions that we're very interested in, and this motivated basically the physics at high angular resolution in nearby galaxies collaboration to form. I'll soon tell you in the next slide how it got started. So the aim there is really to understand the interplay between the small scale physics that can between gas and star formation with galactic structure, and how this links to also galaxy evolution, and then also how this could help understand star formation regions that are happening in our galaxy. So the sample was selected to basically be massive nearby galaxies. So you see them on in the picture here, shown in the star formation rate versus stellar mass plane. The contours outline the background of about 10,000 galaxies in the local volume out to a distance of about 50 megaparsecs. And you can see that there is a density shown in the contours that is so-called the main sequence of star-forming galaxies, because it's been known since about a decade or more, probably even more, that galaxies tend to form stars at have a given stellar. If you know the mass of a galaxy, you could basically predict their star formation rate if they're forming stars. So we really wanted to sample the bulk of the galaxies where the stars that they're currently being formed are forming. So we put down a distance cut of 1 arcsecond, so that 1 arcsecond resolution belongs to 100 parsecs, so still captures 1 star formation unit. Since we wanted to understand the physics, we avoided edge-on galaxies, and since one aim was to have a good knowledge of a molecular gas, the galaxies had to be visible from ALMA, which is a southern instrument. So basically this set the declination range. The people doing all the hard work are listed here. On top, you see the core members. So these were the initial 18, 19 people that said, this is a really good idea. We really should start working on it, and also then put in the effort. The poor people highlighted are the ones that basically said, we will do this and we will convince all the others. And I think we have been very successful in convincing. Below you see the list of the current full members that are associated postdoc students, senior scientists with the core members. And in the middle you see an image of our team meeting in March in Madrid, when it was still possible to travel. So thanks is on the one side an observationally driven collaboration, so getting new data is very important. We also have a number of theorists within the team that help us understand our observations, and I hope to get this point across at a few places. So the main observations, the main sample are now about 90 galaxies observed with ALMA. A large fraction of them come from an ALMA large program that has been finished taking data a bit more than a year ago. Both are complemented by optical H-alpha narrowband imaging from 2 small telescopes in Chile. A subset of the galaxies is observed via an HST treasury program led by Janice Lee, and basically to get multi-band observations of young stellar clusters, so to get the end products of the star formation process. This project is still ongoing and in the middle of its data taking. And a further subset of the HST sample are MUSE, have been observed with MUSE. So this is optical integral field spectroscopy, which gives you full access to H2 regions and their physical and their properties. And that was a large program as well. In the meantime, we've started a program to obtain AstroSat FUV data. So this is the small thing here, and a subset of the galaxies also has H1 data. As you know, the VLA is located in the north, so observing galaxies in the south, not all of them are accessible with the VLA. So just to give you an idea how the observations trace the different phases. So you see ALMA clearly traces the molecular gas through its observations. MUSE gives you access to the H2 regions, but also a lot of information about the underlying stellar population, though I will ignore this in the talk today. And basically HST samples the end phase of the star formation process, so young stellar clusters, but also of course older stellar clusters. And this is only to give you basically an idea of what kind of galaxies we've been looking at. So this is a subset of the MUSE sample, and you see that the galaxies have quite different appearances. And so this is very useful to understand if the influence of the environment. And also just to highlight, so this is was the first HST image was delivered, I think, last year in April. And if you compare it with the ALMA data now shown in red, you basically, you basically see that there you have extinction is where molecular gas is showing up. So after the introduction of the survey, I want to basically focus on today's talk's topics. The one was to understand the physical state of molecular gas, and here basically two observables can kind of convert it into physical parameters. So the line width that one sees at our resolution basically is a good measure of the internal turbulence within a star-forming unit or molecular cloud. And this is basically a measure of the kinetic energy within this star-forming unit. At the same time, if you look at the gas surface density, which is a proxy of basically the gas mass contained in that, and then the mass, of course, is a proxy for potential energy. So this is the set of a snapshot of a subset of the ALMA galaxies we are using. So you clearly see that molecular gas surface density comes in various flavors, likes to orient along spiral arms and bars, but sometimes is also only very flocculent in the disks. So based on this picture, one might expect to see variations in both the surface density as well as the line velocity, dispersion. And indeed, Jai Sun, who is a finishing PhD student at the OSU, working with Adam Leroy, started in 2018 with a subset of 12 galaxies to see if he can see variations. So what you see here is histograms of the surface density of a gas surface density at 120 parsecs. And the thing that basically jumps out is that the distributions are not the same. They are also not peaking at the same locations. And if I guide your eyes, so the cyan boxes are galaxies that have stellar bars, and all of them exhibit a secondary peak push to higher masses. This is basically their centers. The two galaxies, M33 is a very low mass galaxy. In M31, the emission has only been observed in the outer disk. So both are in regimes that are dominated by atomic gas compared to the upper panels that are in regimes dominated by molecular gas. So you see also that the average surface density is lower. And then for reference, just the antennae, which is a merger where everything is pushed to much higher surface densities. So then comparing basically the molecular line width measured versus the surface density, despite both tracing a very wide range in parameters, they form a very close line. And basically for reference, you see these two diagonal lines, which are parameterizing the ratio of the kinetic energy relative to the potential energy. And so basically this plot tells you that the gas is in kind of an energy equipartition, so that it is stable. So the question is, what keeps the gas stable? And this has been basically proposed already by Annie Hughes in 2013 and also others. I refer to her work. And so you can basically understand the cloud internal pressure is set by the turbulence. So the turbulence being, it's the internal line, the internal velocity dispersion. In order to measure the external cloud pressure, the understanding is it's basically the weight of the gas disk and the weight of the stellar disk together. So basically it's the hydrostatic pressure that the two set them together. So this is an idea which can be tested now, given a lot of the data. And this is some new work Jai Sun has been doing and published this year. So he basically measured the turbulent pressure, so the internal pressure at 120 parsecs, and compared it to the hydrostatic pressure that is exerted by the gas and stellar disks together. So the gas disk here is indeed the atomic and the molecular gas disk overall. And the surprising thing is that it is clear there is a correlation. However, if you normalize it, you see that it is offset from the one-to-one line. So all the clouds appear overpressured. So the next thing was basically, it means that something is missing in our determination of the external pressure. And the idea is here indeed that it is the self-gravity. So this new parameter now accounts for the fact that the clouds themselves have self-gravity as well. And now you can see basically, if you compare the two panels, that the clouds are indeed falling onto one-to-one. So one first insight is basically that the internal pressure is indeed regulated by the external pressure. However, it's important to also take into account the weight of the clouds themselves. So it's not only the stellar and the gas disks they are sitting in. But is that the full story? So this is the latest work Jai has done. So he basically extension now using the full target, the full galaxies, so 66, which is about more than 100,000 measurements, to understand basically if the gas surface density is indeed very stable. So what you see here is the galaxies plotted in, again, in the star formation rate versus molecular gas scale. And the color coding is by the average weighted gas surface density. And what you see is like to scatter more for galaxies that have higher stellar masses, and they might have a tendency for also being higher for galaxies that exhibit on higher global star formation rates. The bit that is more interesting and kind of argues a bit against everything being simple is the centers of barred galaxies. You already saw before in the plane where you looked at the molecular gas surface density, that there was a secondary peak in the centers where they were shifted to higher. So here you now also clearly see that they not only have higher surface densities, but they also have a higher internal pressure. And if you compare them to the disk gas, it's very clear. And also if you compare it to the centers of galaxies that don't have bars. Why that is, we don't fully understand, but it's very interesting. The other thing that is very interesting is also that spiral arms exhibit on average a higher molecular gas surface density than the interarm regions. So this might then potentially explain why star formation appears more prominent along spiral arms. However, the reason for this, there's, I think, a lot of discussions also in the galactic community if that could happen and so on. But this is one of the first clear measurements that indeed there is a difference, an observable difference. So basically, the conclusion of this first part, setting the questions, is that the internal gas structure is set by the balance of internal and external pressure. However, it also seems that overall galaxy properties might, they exactly matter is something for the future to be found out. The next part I want to do is basically look at H2 regions, there the interesting points I would like to highlight is basically to understand if we can gain some insights about metal mixing models, and also basically using observations of H2, their variation or how homogeneous they are. So the first, just to introduce metal mixing models, why have they been come? So this is an example of the work by Yiting Ho survey. This is the nearby galaxy 1365, and you can see very pronounced variations in the relative metallicity from the regions, with the arm regions having enhanced metallicity relative to the interarm regions. This has been seen in other galaxies as well, and the references are given above. And this had been motivated basically that this is a sign for pristine gas being moving in flowing inward and being mixed. In his paper, Eating Ho proposed a different model, which he basically called the chemical evolution carousel. So here he argues that it is more the injection of metals in the spiral arms that cause an injection, and then this kind of gets diluted once it's mixed with the downstream material. So basically it means the gas comes in, has its enhancement on the spiral arm, and once it leaves the spiral arm, it's getting diluted. Is here basically the idea. Now with MUSE, we basically have the opportunity to take molecular, look at the H2 regions and their metallicities. And this just gives you a snapshot of the variety of the data you can get here. Catherine Krekel has used the 8 galaxies for which we had full mosaics to look into this. So here you see the H alpha emission, and on the right hand side you see the inferred metallicity. So you see a clear gradient where the center has higher metallicity versus, and this decreases towards the disk, and this is the radial gradient that's long known. This galaxy already exhibits azimuthal variations. For reference, this is a 500 parsec element in this galaxy. So by looking at these 8 galaxies, Catherine was basically asking, if I look at the galaxies that relatively to the average radial gradient have a reduced metallicity versus the ones that have an enhanced metallicity, how do they distribute if I look at the ionization parameter traced here by sulfur lines, cluster H by looking at brightness in H alpha versus brightness in far UV, or molecular gas density using basically the CO intensity, or the mixing, or assessing the mixing level by saying regions that exhibit a lower velocity dispersion are potentially younger than the ones that have a larger one. And if you put all that together, so you assume younger H2 regions have a higher paraionization parameter, are still more embedded in their parent molecular cloud, have a higher H alpha over FUV ratio, and are more lower velocity dispersion, you would come to the conclusion that basically that this could be then taken as an evidence that that there is evidence that local enrichment is happening by recent star formation, given these parameters together. The second aspect of its paper was to see how abundant azimuthal metallicity variations are, and if they can be linked to the presence of spiral arms or some other clear patterns. So this is a subset of the 8 galaxies shown here. These are the ones that show the clearest sign of azimuthal pattern variations, and also that sometimes they seem to be linked to the presence of spiral arms, but not always. So the conclusion is there is azimuthal variation, but it's not always happening. So this raised the question, since the metallicity determination was done using strong lines, if this has been is indeed the correct tracer, or if we maybe are misunderstanding. So this is one spiral arm in NG 1672. On the arm, there's higher metallicity. Downstream of the arm, there is lower. And so Eating Ho took that same data set, and for a subset of H2 regions, they were strong enough that aurora lines could be detected from neon 2. And these lines have the advantage that one can indeed derive an electron density from them. And what you see here is the spiral arm, as I showed it before. These are the subset of H2 regions for which a high temperature could be found. an intermediate temperature and a low temperature. And it's very striking that the H2 regions with a low temperature, which argues for enhanced metallicity, are all sitting on the spiral arms, where the ones with higher temperatures, which argues for reduced metallicity, are on lower arms. So this made us very confident that we are indeed seeing as observed. Another aspect of this was when we saw variations in the metallicity in azimuth or in the scatter. And so how large is the coherence length, basically, or the scaling length that we scatter is roughly is lower. And so basically Catherine measured in apertures going from a few hundred parsecs, 300,000 parsecs, and see. And one sees is that the scatter is lower for smaller apertures than for large. Basically, if you just take all your measurements and you sample them, so this is the null hypothesis. The thing that was then interesting, if she started to focus on the regions with reduced metallicity, you still observe the trends, except for one galaxy, but you didn't see any trend in the when looking at the regions with enhanced metallicity. So this then argues that the H2 region metallicity is very homogeneous on small scales, but that this is indeed true metallicity regions. And this was then the argument is more in line with the carousel model for mixing than having gas inflow, because you would expect that the inflow of a pristine gas, you might have more variation in there. This basically concludes that part of the talk, and this is now the last part that I will spend more time. So this is about process. So the question is, how is star formation distributed, and what is the star formation process? So one can now do just a very, very simple experiment, and this was work that I published a year ago, and this work, and we asked a very simple question. If we take a map of molecular gas, you see on the left, and of the H-alpha emission, which we take as a tracer of the star formation, how often do we have sidelines where we find both tracers? How often do we have sidelines where we only find either molecular gas or star formation, and how are they distributed? And this is basically what you see in the right-hand side. Only tracers being in dark blue. The overlap, where we have both tracers in the kind of pink color, and red, where you only have star formation. And did just some simple accounting per galaxy, now showing in pie chart the fraction of the sidelines. It became very clear that there is a significant fraction of the gas that is quiescent, or the sidelines. It persists in flux, basically, if we ignore galaxy centers, which seem to behave more differently. And also, it's often the most abundant fraction. And this basically, if we take, for example, the H-alpha lifetime as a clock, then you can just use these pie charts and derive a gas consumption time, and you find that it is about a few 10 million years on average. So this work now has been expanded by Xiean Pan, who's a postdoc with me at MPIA, to 51 galaxies, where this now can be done at 150 parsecs. And now it's more interesting because we can study the effect of parameters like stellar mass, for example. So down here in this rather busy plot, you see in blue the CO only, so the molecular gas only sidelines, the sidelines where we only see star formation in the form of H-alpha, and the sidelines that overlap. And she has broken up the sample into 3 mass bins, from low mass, intermediate mass, and high mass. Light colors are low mass, dark colors are high. light colors are low, dark colors are high mass, and the bright colors in between are medium mass. So the interesting bit is that the fraction of sidelines with overlap don't evolve with stellar mass. However, for molecular gas, you find much more molecular only sidelines in high mass galaxies compared to low mass galaxies, and the inverse trend is basically visible for the star formation. So one question was, so is that just a global property, or do we also see it as a function of radius? And these are now the plots, again, as a function of radius. So per radial bin, you see the distribution of low mass galaxies, intermediate mass galaxies, and high mass galaxies. This is again for the molecular gas only, H alpha, and basically the same persists. There's basically no variation in the overlap sidelines, but a strong variation in both the molecular gas and the star formation sidelines. And interestingly, the question is, what happens if you only have data at lower angular resolution? So basically, if you go from the 150 parsecs, where the separation is very clear, go to typical resolutions of about half a kiloparsec or a kiloparsec, you see that for the CO sidelines, the difference becomes much less to observe, and the same is true, even more true for the star-forming galaxies. And for the overlap, is basically, this is also where the Schmidt-Kennicut comes into place. You don't see a large variation. So this also explains why, if you go to higher resolution, your scatter is becoming larger when you compare star formation rate to molecular gas. So I think this tells us something, that indeed it depends which galaxies we are observing, how the tracers we have behave, but also it should tell us that also we need to go to this very high resolution to observe these results. So one other aspect is about how efficient is the molecular gas to basically in converting to stars. So there has been a theoretical model that has been proposed, for example, by Mark Krumholtz, and this is the so-called star formation efficiency per freefall time. This is basically the star formation rate per mass of a molecular cloud times the freefall time of a cloud. And from theory, basically expectation is that this number should be about 1% once when it's averaged across a full disk of a galaxy. So as part of the early time and to understand, Diaz Utomo, who has been a postdoc with Adam Leroy at that time and is now a Jansky Fellow in Charlottesville with NRAO, he's looked at this, and these are the measurements he got varying for 12 galaxies, varying the resolution of the galaxies, and also checking different assumptions about what to use for the star formation rate tracer, for assumptions on the disk scale height, how complete our detections of molecular gas are, the conversion of our tracer into molecular gas, as well as the sites. And you see the measurements are fairly robust against all these assumptions. It's about 1%. And on top, you see measurements from our galaxy. And so overall, you can see that molecular gas tends to be very inefficient in transforming itself into stars. So one question is there another way to test that, so more directly, rather than doing these overall? So for this, Catherine combined basically NGC 628. Here you see it with MUSE. You see the red green dots are planetary nebulae. And you see in more white the H2 regions, which are basically prominent H alpha O3 as well as S2. And NGC 628 is kind of a twin or a close sibling of M82. It has very large grand design spiral arms. However, it has a surface brightness is about an order of magnitude lower than M51. So here you see about over 1,500 H2 regions, which are detected and compared. And also in blue, now you see the molecular gas relative to the H-alpha emission. For that, we could extract about 800 clouds, about now was how many of these clouds shown here in blue do coincide with H2 regions shown here as orange circles. And Catherine basically counted how many of the clouds do coincide with H2 regions and do overlap and how not. The surprising number was that only about 10% of the clouds could be associated with H2 regions or contained H2 regions. And if you compare the star formation rate of those clouds, as you infer it from H-alpha, to their molecular gas mass, these are the dark black points, and compared to other measurements that you've seen in the LMC in orange or the nearby low mass galaxy NGC 300, they are really offset. So those clouds seem to be less efficient in star formation. It's not as bad if you compare it to galactic data points, which are all the crosses. So it's very clear that the conversion of gas into stars is not very efficient, and it also varies between a high mass galaxy like NGC 628 and more low mass dwarf galaxies where the study has been done. And the last result I want to show is by Melanie Chavance. She has been combining also H-alpha data with CO data to infer how long molecular clouds can live. This is basically if you make the assumption, how often do you find these two associations, and put this into the framework of the uncertainty principle as it was developed by Diederik Krijsen, and you see this similar applications also from a number of other authors here. And what she basically infers is here, so here's the 0 point, here's the phase of the H-alpha that is not associated with molecular gas, and here you see the others. And you basically now can read off what is a typical lifetime of a molecular cloud, and you find that it is about 10 to 30 million years, which is consistent with the previous studies listed up there and also with other methods. Overall, the orange color, which shows basically molecular gas only phase, is relatively long to what is the feedback phase, where you basically see molecular gas and star formation at the same time, which barely reaches larger than 5 mega years, which tells you that supernovae cannot be a strong source of feedback, because typically supernovae are expected to reach their largest impact after 10 to 30 mega, in the range 10 to 30 mega years. So these were a number of results. There have been more papers are coming out of the collaboration. I list a few. The one on top are mostly submitted and hopefully will appear on AstroPH soon. The one on the bottom are the ones people are working on, which are utilizing more of the full sample, also provide data products which might be of interest to other people. If you have more interest, I suggest you check out our webpage, and I'd like to end here. So I think the points I would have wanted to make are that for the star formation process on cloud scales, you really, to understand it, you need to reach the scales of the star forming units. I think that is demonstrated now. That's where differences within and between galaxies become apparent, both for H2 regions as well as for looking at molecular clouds. Molecular gas within galaxies tends on, when observed at these scales, to be close to energy equipartition. However, the global as well as the local properties still matter, and we have a twist on the exact distribution. And star formation is clumpy, inefficient, but when it started, it proceeds fast. And I also would like to have a big thank to the staff at NREO, JEO, ESO, and SDSEI, who have been very supporting for the preparation, conduction, and also delivery of these unique data sets, and also in general more of all their efforts that they helped us to assemble this data set. So thank you very much.
Thank you very much, Eva, for this very nice and complete seminar and colloquia. And now the talk is open for questions. For all the participants, please raise your virtual hand and I will give you the word. Isabel? You are mute.
Excuse me. Yeah,
Okay.
I know, but I was trying to get my mouse. I having trouble with it, with the two screens all the time. Thank you very much, Eva. It was really amazing, all what you have shown. I'm really interested in the sample, so I will have a look on. I had already have a look on the web page, but not deep enough, I think. So I'd like to ask you how, if there is any way of knowing if you have probably already explored. How many galaxies do you have showing active galactic nuclei, and what's the environment of the FANGS galaxies in general? If you cover all possibilities, or you are restricted to something special?
So a number of our galaxies have AGN. I don't know the number out of the top of my head. A bachelor student who's writing up her work, she has been looking at that and compiling. If I had to guess, I think it's about 20% that have an AGN. Regarding environment, our restriction was indeed driven by distance, as I guess people working with nearby galaxies know. Knowing the distance of a galaxy is a very difficult endeavor, particularly if you go beyond 5 megaparsecs or 10, there the distance measurements become highly uncertain. We tried to restrict the sample to about 70 megaparsecs. We have a couple of galaxies that are further away. It's particularly galaxies that are sitting in the Virgo cluster. Mm-hmm. And so we have galaxies in the Virgo cluster because that's one of the regions we have most galaxies outside. Then we did the sample selection. We missed some galaxies that should have been in the sample. We included some that should be not. A lot of this will be discussed in Adam Leroy's paper that describes the ALMA survey and also the sample selection. Yeah, so this paper, we're working hard. We would have liked to have it submitted in the summer, but I think it will be before Christmas for sure, because that would be the big description of also all the ALMA observations we've done. We have also started to observe the nearby big galaxies like NGC 253 or so, with a dedicated follow-up program, which is led by Chris Fazy. And also there has been extension to a few more early type galaxies, but I think most of them are also more covered by the Wisdom sample, which is led by Tim Davies and Marta Bureau. So,
okay, thank you very much.
Thank you. Any other question for Eva? Ute Senfeld, please go. Ute, you need to unmute your micro.
Thank you. Yes.
Okay.
Okay. Thank you very much for this very nice overview of this tremendous work and these wonderful results. All the results with respect to the molecular gas are based on CO2-1, isn't it? And my question then is, in the recent years, there have been a number of papers coming out that showed that CO2-1 and CO1-0 is not always constant in galaxies. Does this have an effect on your work, or did you look into that? Could you comment on that?
We are aware of this. I think there's some study from the Empire that is working on this. Overall, the variations seem, there are galaxy to galaxy variations, and the variations within galaxies appear a bit lower. If you look at kiloparsec scales from Empire work, so that is work by a student, Jakob den Brock, who's working with Frank Bigel in Bonn. And that paper is currently under review. There is Toshiki Saito, who's a postdoc at MPIA, is looking at a subset of 4 galaxies where with 0, 1 to 0 and 2 to 1 is available at about 200 parsec resolution to understand if there are variations. So we see variations. It seems to be that the ratio is higher where there is more star formation. What this exactly means for the conversion factor, we don't know. I think if you believe models by Paul Clark and Simon Clover, it might cancel out if you're lucky. So in that sense, it's an uncertainty. I don't know if the lever arm between 1 to 0 and 2 to 1 is large enough that you can do good enough physics. Also, I think people have to prove that the absolute flux calibrations are good enough also that you can do strong trends. The variations we see, some of them, they are fairly robust, so I would expect they are potentially larger than just being an effect of a conversion factor.
Okay, thank you. Thank you for this.
Thank you. More questions to Eva. Okay, seems there is no more questions. Thanks again, Eva. Oh, here.
Thank you.
Here, another question, sorry, Isabel.
Yeah, excuse me. It's just a brief question, and it's probably you already took that into account because you didn't take very galaxies with high inclinations. So, but when you put the plots, when you superpose H alpha and CO, those are projections, superpositions in projection, right? So have you got any idea of whereas you can have any effects of having a 3D view of those superpositions?
So for this particular galaxy, it has a very low inclination of about 20 or so. So there the offsets are indeed real. For M51, we also saw this along the spiral arms. I think it's kind of makes sense if you expect that the dense gas or that the condensation of the gas is happening in the spiral arm, in the potential, and then it takes a certain amount of time till it moves off. The numbers, when we calculated them in 2017, I believe, they didn't come out as a totally clear cut, so potentially other effects like magnetic fields might play a role as well. Mm-hmm. There is a trend that there seems to be more an offset between the two. If you go to, or between star formation and molecular gas more, if you go to very high resolution, we haven't come up with a good methodology that we can apply directly to all the galaxies and in a homogeneous way. It's challenging. Galaxies look kind of like they are nice, have nice spiral arms and so on. If you start to look in detail, you realize that spiral arms don't follow perfect spirals and so on. So you have to take all of that into account, and it's not so easy to do. So I don't know if that answers part of your question.
Yes, of course, yes. Yeah, it's, I mean, just seeing the images, we see that real life is much more complicated than we would like to in principle, but it gives also the opportunity of studying in more detail. So that's great. It's amazing what you've shown. Thank you very much, Eva.
Thank you. So if there is no more questions, we can close this colloquia. And thank you again, Eva, for giving us this talk.
Thank you for the invitation.
And of course, you are invited again to Granada to come here.
Thank you.